So the last math concept we're going to go over is constrained optimization. So the basic idea is that there's some function that we're trying to maximize or minimize. Okay? And let's say that that function is some function f of x and y. And we're maximizing or minimizing the function f subject to some constraint g, or some function g of x and y is less than or equal to some constant d. Okay, so for example, this function f here could be the utility function. And this function here, this g of x and y, is something like the expenditure function, how much a person is buying. And the idea is that this has to be less than their income, which might be represented by d. Okay, so that's the basic setup. We're going to assume, for simplifying purposes, that the constraint is always exactly satisfied, which implies that this less than or equal sign is actually going to be, in our problems, replaced with an equal sign. That's going to simplify things a little bit. In economic problems, that always seems to be the case. So for example, by the more is better assumption, consumers always like more stuff. And so they never want to leave some of their income unspent in the if there's no future period they're saving it for. In that case, they could spend that remaining income on some more of one of the goods, and that would make them better off. So in practice, often this constraint is an equality rather than an inequality. Okay, so we're going to use two different methods to solve these types of problems. I'm going to show you an easier method and a harder method, where the harder method has some advantages. So the two methods are the substitution method and the Lagrange multiplier method. Okay. Okay. So we're going to look at this one, the substitution method, first. And the basic idea here is that what we're going to do is we're going to use this constraint to find some relationship between x and y. So we're going to get, for example, x as a function of y. And then we're going to plug that in. So let's say we find x of y comma d. So it's x is some function of y and d such that the constraint exactly holds. And then we're going to plug that, actually let me use a different color. We're going to plug that in for x into this equation. And now we have this initial equation in terms of only one variable, y. And so we can solve it as usual. So the basic idea here is that it's the value of x that exactly satisfies a constraint conditional on the value of y. So for example, in a consumer's utility maximization problem, we could find the amount of x that could be purchased with remaining income after some amount y has already been bought. Right? Some amount y costs a certain amount. We could see how much income is left and how much that remaining income would buy, how many units of x it would buy. That's the basic idea. So let me just give one more slightly more specific example of the substitution method. Let's say that the constraint is actually this in black is x plus y is equal to 1. So we could rearrange that to find that x as a function of y is equal to 1 minus y. Right, so take some value of y, plug it into this function here, and it tells you what amount of x would be such that this constraint exactly holds. Okay. So let me go over one other problem where I actually go through all the steps of maximizing a function subject to a constraint. So let's assume, all right, over here, that the function that we're trying to maximize is equal to x times y. And the constraint is that 2x plus y is equal to 6. And now we're going to solve this using the substitution method. So the first thing that we're going to do is we're going to use this constraint here to find the relationship between x and y. And so if we just subtract 2x from both sides, this yields that y is equal to 6 minus 2x. So this is just a rearranged constraint. So rearranged constraint. Then we can plug in, so then plug into the function that we're trying to maximize or minimize, which yields that the thing we're trying to maximize or minimize with this plugged in is x times y, which from this part here we know is equal to 6 minus 2x. Now we have this thing that we're trying to maximize or minimize written in terms of one variable x, and we've plugged in for y, assuming that the constraint is exactly satisfied. So this is this part right here, I should be clear, is the amount of y that satisfies the constraint conditional on x. So then all we do is take the derivative. So we're going to take the derivative of this whole function, x times 6 minus 2x, with respect to x. And that gives us 6 minus 4x. Again, we always set the derivative equal to 0 when we're solving these problems. If you rearrange this, you would get that x is equal to 3 over 2. You could then plug this value of x back into the constraint, and you would find that, let's see, so y is equal to 6 minus 2 times x, so y is equal to 3. And again, you can plug these back in to find what the maximized value of the function is. It's 9 over 2. So that's it. That's a substitution method. You start with the constraint, you rearrange it to solve for one of the two sort of input variables into this function you're trying to maximize or minimize, right? And then you plug this in, for that variable, in the function you're trying to maximize or minimize. And now you have that function only in terms of one variable. So now you can just take the derivative with respect to that variable, set it equal to 0, and then go back and find the value of the other variable using the constraint. So that's the easier of the two methods to solve a constrained maximization problem or a constrained minimization problem. Now let's look at the other method. The other method is the Lagrange multiplier method. Now, this method is always going to involve the same steps, and the only thing that you need to do is to learn these steps. I usually like to give more intuition for exactly why we're using a certain method, and I did used to do that for this problem, but I found that trying to sort of pack what is actually a somewhat longer lecture from the linear algebra class, it's like Math 15 or something like that, into 10 minutes of my lecture was just not a great idea. So what I do is I teach you the steps. So we're going to do that. So the first step to solving the Lagrange multiplier problem, or to using this method to solve a constrained maximization problem, is you're going to write down the Lagrangian function. Okay? For now, I'm going to represent the Lagrangian function with an L. And it's going to be equal to the function that you're trying to maximize or minimize. So some function of x and y, plus what we call the Lagrange multiplier, which is represented by the Greek letter lambda, times the constraint. Okay, now here's kind of the tricky thing. In the previous few slides, I said that the constraint was that some function g of x and y was less than or equal to d. How can we plug this in without adding an equal sign or less than equal sign? We want this to be some function, not something with an equal sign or an inequality right in the middle. So what we're going to do is we're going to rearrange this constraint to something that's equal to 0. And we're going to plug that thing that's equal to 0 into the Lagrangian function. So let's do that. So we're going to rearrange this, and basically what you do is subtract the g function from both sides, getting that d minus g of x and y is less than or equal to 0. And you take this part here, and this is what you plug into the Lagrangian function. Okay, so we're going to have the Lagrange multiplier lambda times d minus g of x and y. It's basically the constraint rearranged to something that's equal to 0. Okay, so this is the Lagrangian function. It's basically the thing we're trying to maximize or minimize. Then there's this Lagrange multiplier, which is essentially a penalty parameter. Once we include this penalty parameter and multiply it by this constraint rearranged to be equal to 0, it means that if we maximize this entire function with respect to x and y with the right size penalty parameter, then it would be the same thing as just maximizing this function f subject to the constraint. Okay. So what we want to do is we want to find the value of the Lagrange multiplier, the right size of the penalty. We actually solve for all three of the elements, x, the y, and the lambda, together through the same series of steps. Okay. And the way that we do that is we're going to take the partial derivative with respect to each of these three variables. The two variables that we're trying to maximize with respect to x and y, and then this penalty parameter lambda. We take the partial derivative, set that equal to 0. We're not actually maximizing over this, and I'll come back to that a little bit later. I'll talk, but it's still the same solution steps. Okay, so let's write down these three partial derivatives. We're going to take the partial derivative of the Lagrangian with respect to x, and we're going to set that equal to 0. We're going to take the partial derivative of the Lagrangian with respect to y and set that equal to 0. And then we're going to take the partial derivative of the Lagrangian with respect to the constraint lambda and set that equal to 0. And that's basically just going to return the constraint. Okay? And then we're going to look for the values of x, y, and lambda such that all three of these equations are satisfied. So each of these three partial derivatives are equal to 0. And that's it. That's the steps that are involved in computing the Lagrange multiplier method. So let me erase a little bit of this here. And then let's go back and we'll solve that same problem that we just solved using the substitution method. We'll solve it this time using the Lagrange multiplier method. So let's say, again, that the function we're trying to maximize or minimize is f of x and y is equal to x times y. And in this example, we're trying to maximize that. And the constraint is that 2x plus y will be less than or equal to 6, but we assume that all these constraints hold with equality, so we're going to say equal to 6. Okay. So to solve this using the Lagrange multiplier method, the first step is to take the three partial derivatives. So we're going to take the partial derivative of, first step is actually to write down the Lagrangian. I forgot that step. So the Lagrangian in this problem, it's always equal to the thing that we're trying to maximize or minimize first. That's what goes into this first part of the Lagrangian here. Okay, don't rely on functional forms, because sometimes things that sort of look a certain way will be the thing you're trying to maximize or minimize that appear here. You always just want to put whatever you're trying to maximize or minimize first, and then the constraint is what is multiplied by lambda. Okay, so the thing we're trying to maximize or minimize in this problem, trying to maximize x times y. And then we're going to add to that the Lagrange multiplier lambda times the constraint, rearranged to be equal to 0. So that rearranged constraint is just going to be 6 minus 2x minus y. So this part here is the Lagrangian function. And that is the function that we're going to use to take these three partial derivatives. So the first partial derivative, I'm going to take the partial derivative of the Lagrangian with respect to x. And that's just equal to y minus 2 times lambda. And again, we set these partial derivatives equal to 0. The second partial derivative is the partial derivative with respect to y. And that gives us x minus lambda is equal to 0. And the third partial derivative is the partial derivative of the Lagrangian with respect to lambda, which just returns the constraint. 6 minus 2x minus y is equal to 0. Okay. So the way that I'm going to solve this, there's a couple different ways you can solve it. I mean, basically, any way where you solve these three equations for the three unknowns, that is, find the values x, y, and lambda, so all three of these partial derivatives are 0, any of those methods would work. I'm going to show you one way right now. I'm going to rewrite equations 1 and 2, calling the rearranged equations 1 prime and 2 prime. For each equation, I'm just rearranging it and solving for lambda. So we're going to say 1 prime. And that is going to be equal to, so we're going to yield lambda is equal to y divided by 2. Okay, so all I did here is I added 2 lambda to both sides, divided by 2, and that gave me this rearranged equation 1. Now I'm going to do the same thing for equation 2. I'm going to rearrange it to solve for lambda. And that one is simpler. It just gives us that lambda is equal to x. Okay, so now I'm going to use these two equations. We know that lambda is equal to y over 2. Lambda is also equal to x. So we can combine that information and say that y over 2 is equal to x. That's just combining the information from equations 1 prime and 2 prime. Okay. And now we can use that information and plug it into the third equation. Now, before we plug in, this third equation depended on 2 variables x and y, so it alone was not enough information to help us solve for either of those variables. But once we plug in for x, then this equation is only going to be in terms of one variable y. And so we're going to be able to solve for y. So let's sort of combine these two pieces of information. And that gives us that 6 minus 2 times x. But remember, x is equal to y over 2. So plug that in. Minus y is equal to 0. Which gives us 6 minus y is equal to 0. Or y is equal to 3. Okay? We could then plug this back into equation 3, which is the constraint, and we would get that x is equal to 3 over 2, and so on. Now, these solutions should look similar to you. They're the exact same solutions that we got when we used the substitution method, which should be the case. Okay, you could also solve for lambda. If you recall from the step equation 2 prime, we already figured out that x is equal to lambda. So we know that x is equal to 3 over 2. Hence, lambda must also be equal to 3 over 2. So it is expected that you are able to use the Lagrange multiplier method to solve problems. That could be something you're asked to do on a midterm or final. It could say that to get full credit for this problem, you have to use the Lagrange multiplier method. Basically, for the sake of this class, you just have to make sure that you know the steps. The reason that we learn this method is that there are some advantages to it. So first of all, the value of lambda has some meaning. It means it is equal to the derivative of the thing you're trying to maximize or minimize. So the derivative of this maximized value of this f function with respect to the constraint, with respect to d. So if in the consumer's problem, the value of lambda tells us the derivative of consumer utility with respect to the amount of income that they have. So it can have a meaning that is useful in these problems. Additionally, methods like this can be actually easier to implement if you're solving more complex problems using a computer. So I'm not going to really get into the details of that, but for more advanced problems, the Lagrange multiplier method can be more useful. And even for those of you who will never, or who at least now never plan to use those more advanced methods or program into a computer, it is still useful for you to be able to communicate with people who do that. Okay. The last thing I wanted to mention in this short video is that we are not maximizing the Lagrangian function with respect to the three variables x, y, and lambda. Rather, we're maximizing with respect to x and y and finding the value of lambda that's sort of the right penalty for this. And it's easy to illustrate that we're not maximizing with respect to all three variables. Because if we were, it would be very easy to get this Lagrangian function to go to infinity, to a really large value. For example, suppose you chose the values of x and y so that g of x and y was less than d. Then this part here inside the parentheses would be greater than 0. If that's the case, you then choose a value of lambda that's equal to infinity, and the value of this entire Lagrangian function is infinity. Okay, so clearly we are not choosing the value of lambda to maximize the value of this Lagrangian function. Rather, this method works to find the value of lambda that's the right penalty for solving this problem. Okay, so that wraps up our math bootcamp lectures. I'm going to go over a couple other related problems, practice problems, and other related things in class. See you there.